I guess he's recording now.
Yep.
Great.
Okay, please start, Chris. Thanks very much, Lorenzo, and yeah, welcome to Lancaster, everybody. We put some good weather on for you today, but I can't guarantee it's going to last a week. So make as much as we can of it this evening. Yeah, so welcome to the masterclass on parallel computing. I guess this idea came about because Lorenzo and I were sort of chatting about thinking, you know, what have we done in Bayes for Health and wider in cosines? What's the sort of methodology that we've cooked up over the last few years, and how could we more effectively try and get that methodology out into some implementations so that people can just pick up software packages and use it, hopefully. So Lorenzo and I have been doing quite a lot of parallel computing. For those of you who don't know, the reason why I'm attached to Bayes for Health is because my research centres around epidemic inference and prediction. And I come from a background where we use very high dimensional models, which are very computationally intensive. And parallel computing, I think for me, really from the get-go when I started circa 2006, has always been a necessity. So I've worked with a range of styles of parallel computing. I've had some, greater success with some, less success with others. And so Lorenzo sort of asked me if I was to kick off by kind of giving a sort of summary of what's out there, the sorts of kind of hardware that we might want to think about when we're doing parallel computing. And it was quite interesting thinking about this, actually, because the landscape's a bit different to when I was a PhD student, actually, and hopefully we'll sort of pick up on that as I go through. So what I thought I'd do is we'll start off and sort of aware that everybody in the room here is a statistician, right? So not necessarily a computer scientist. So I thought I'd sort of motivate this by giving a little motivating example, just of placing pi using the Monte Carlo approach, and use that to sort of motivate discussions for thinking about how CPUs work and what's out there and the sort of pros and cons of different types of architectures. Right at the end, this kind of item 5 is very much a kind of if there's time and if there's inclination. It's a separate slide deck and work that I did quite a while ago when I was getting into GPU compute, but I think it kind of hopefully fills in a little bit of background, probably to me as somebody who was facing a solution to a problem, and a bit of a story as I went through. I'm table to 315, is that right?
Yes.
Yeah, so I am definitely not going to use all that time. And the point about separating out item 5 is that we might want a bit of a comfort break by then. So we'll just see how we go. We'll wing it and see what happens. Okay. Who in the room is kind of sort of Python familiar? Most people. Okay, that's great. Right. Okay. So here's my sort of motivating example. Okay. Suppose we're, kind of first, maybe second year maths stats student, and we've been tasked with working out a method to compute pi. This is like canonical parallel example. So the one way that we could do this is via a Monte Carlo sampling exercise. So the idea is that we have a square which has origin right in the center here, and then it's 2 unit by 2 unit square. So 4 square total, and the idea is we're just going to throw down uniformly distributed points within this 2 by 2 square, and then we're going to see if those points fall within 1 unit of the origin. Okay, so quite a sort of simple example, and then hopefully I can use the proportion of squares landing in this circle It's going to tell me something about pi, give me an estimate of pi. Okay, so how could I go about implementing this? Well, perhaps what you might think of doing if you're a programmer, Python programmer, is first of all defining a function that generates a random point and checks whether it falls within the unit circle. Okay, so that's fairly straightforward. So suppose it takes a random seed. Okay, I'm going to use that seed to generate my uniform random variables in the x and the y direction. Okay, and I'm going to first of all start off by splitting this seed in two. So split the seed in two. Darren's going to talk way more about this. So I'm just going to kind of skip over seed splitting for now. But we're going to split it in two, and we're going to put one half of the seed into our x direction uniform sampler and the other half into our y direction uniform sampler. Okay, so I come up with two random variates, x and y, and then just simply see whether the magnitude of that vector of length 2 is less than 1, and it returns a Boolean. Okay, true if it's in the unit circle and 0 if it's not. Okay. So what I quite like to do then is actually to execute this function, a large number of times. So I've sort of split this algorithm into 3 steps now. So step 1 is a kind of a setup phase. Okay, so we're saying that, our size of our Monte Carlo sample is going to be 1 million. We're going to create a range of seeds that we're going to feed into our in-circle random number generator, okay, of length n. So that's our kind of setup phase. So a scalar and a vector, essentially. And then in step 2, just in case people aren't familiar with this syntax, this is a Python list comprehension. And basically, you can think about it as an old-fashioned for loop in a way that I could write on a page and didn't create huge amounts of code. So what this is doing is it's running the in-circle, executing the or applying the in-circle function along this vector of seeds. Okay, so I should get, if this works correctly, a list of 1 million trues and falses in this thing that I've called Z. Okay, so think of step 2 as a for loop. And then in step 3, I'm just going to take that vector of trues and falses. I'm going to coerce the trues and falses to 1s and 0s respectively. And then I'm going to take their mean, which will be the proportion of points in the circle, and multiply by 4 and then return my estimate. Okay, and importantly here, okay, I've got a scalar multiplication here 4 times, and then a sort of scalar function mean, or something that returns a scalar. And then I've got this operation, this print operation down here. And print, as we all know, is just going to print the value of what's in this thing called pi out to the screen. Okay. All right. So far so good. We could do that. We could all go away and we could implement this thing and run it. But the 2 things to note really are, first of all, so this list comprehension thing, if I wrote it out forehand, in longhand as a for loop, okay, I'd probably have an index I that goes from 0 up to n-1 in this case. And I'd use that index to index, first of all, the seeds vector. And then I'd use it to index into some kind of storage array for my results, which might be Z. Okay, so x0, I equals 0, I equals 1, I equals 2, etc., etc. Now, the point about that for loop is that none of the loop iterations depend on each other. Okay, so iteration 1 doesn't depend on iteration 0. Iteration 2 doesn't depend on iteration 1. So on and so forth. They're all independent. So actually, it doesn't matter which order I execute my in-circle functions in. Okay, all I need out at the end is just a jumbled up array of the truths and falses in the right proportions. So that means actually, if I had a million processors, I could give each processor the job of executing one instance of the encircle function with its accompanying seed. And if I did that, then hopefully I wouldn't have to wait for a million times the length of encircle to execute. I'd just wait the time that it takes for encircle to execute over all processes. Okay, so what have we actually done in this algorithm? Well, so step one, I sort of called it the setup stage previously, and actually this is not quite what goes on under the hood in Python, but notionally at least, I've sort of executed this thing. It's completely serial. I have to assign a number to a scalar variable, and then I have to create this vector of a million random seeds that I'm then going to feed into my encircle function. Okay, so it's kind of serial setup. There's nothing I can do about that. I just have to just bear with it. Okay. Step two is what the parallel computing people will call a scatter operation, at least in parallel. So we would be scattering that vector of seeds amongst, if we had them, our a million processes. Okay. So you can think of a scatter operation as going from a sort of a serial thing to a parallel thing. And the other thing that I've just argued for is that actually, because this encircle or this sort of notional for loop inside the square brackets doesn't have any dependencies. It doesn't matter which order we execute these kind of unit iterations, if you like. We can parallelize our for loop over the processes. Then step three is our sort of gather or reduction step. Okay, so the idea behind gathering means gathering the results that each of our sort of parallel processes has generated and pulling them together, perhaps onto some kind of master process that's running. And then the reduction thing is is taking this vector of a million truths and falses and essentially taking their mean, reducing them down to a scalar. Okay. So you'll see those terms scatter, gather, reduction appear all over the parallel computing literature, and it's worth kind of just really knowing what they mean. In the second line of step three, I've got this print statement, and a print statement is an input-output statement. Okay, we're not inputting and outputting to the disk, we're inputting and outputting, specifically outputting to the screen. Okay, but since there is only one screen that we're sat in front of, this has to be a serial operation. Right? And it takes time. It takes time to load it takes time to construct the string that we want to represent. It takes time to represent that in the video buffer, and then for the video buffer to update the screen. Okay, and that has to happen in serial. There's no way around that. Okay, so that's our example. We've got two serial steps here, at least notionally. Our setup step and our kind of gather, reduce, print step, and then we've got our parallelizable step somewhere in the middle. Okay, so I like sailing. So I always take this quote. So I think this was a quote that was kind of an anonymous attribution which came out of the Royal Navy in 1940. So conveying supplies, food, weapons, raw materials from the States to the UK was done during the Second World War in convoys. So these were groups of ships that would travel across the ocean all together, a bit like a parallel processor, each carrying its bit of data. Okay, and it was done to enable sort of defence of these merchant ships. But really, you could only send a convoy as fast as its slowest ship, because if the convoy went faster than the slowest ship, then that ship got left behind and verily sunk. Okay, and that's a really important thing, I think, to remember in parallel computing, because if we've got groups of processors that are all, carrying their bit of data, like, if one of them is lagging behind, then all the other processors have to wait for it to catch up. Okay, so that leads us on to something called Amdahl's law, and Amdahl's law really talks about how algorithms scale in response to changes in compute resource. It's actually a very general law, and that those changes in compute resource are not necessarily just the number of processors that you have at your disposal, but the special case of it kind of packs down quite nicely to sort of explain how we might think about a parallel algorithm. So what I'm going to propose is that we've got a serial algorithm, like the one I've just written down, where we have this kind of iterative for loop, okay, that could be run by a single processor. And I'm going to say that supposing there's a proportion P of the instructions, the machine instructions contained in your code that could be run in parallel. Okay. And then supposing that I have access to a machine with M processors on it. So it doesn't matter whether it's M CPUs on the same box, M computers distributed around the world, or 4,000 cores in a GPU or something. Okay, the idea is just have these M notional processors. And then we've got this function capital T, okay, which is really the execution time of my algorithm. And what I want to know is how the execution time of my algorithm scales as I increase the number of cores. Well, the proportion P, okay, so T brackets 1 is the time my algorithm would take under serial execution. Okay, so time it would take one processor to run the algorithm. So the bit of that algorithm, the P times T1, the bit of that runtime that's parallelizable, should scale as 1 over the number of processors available, right? And then we're stuck with this serial proportion of the algorithm, 1 minus P times T1, that we can never do anything about, because inherently, it's printing to the screen, or it's writing to the disk, or it's doing that kind of sort of setup and tear down of my compute environment. Okay. So you can rewrite this then and just think about, well, what's the sort of theoretical speed up I'm going to get from, employing M processors versus 1 processor. Okay, and you get an expression like this. And the point that this is making is that there's a theoretical limit on the speed up that you can expect from your algorithm, thinking asymptotically as n tends to infinity, and it's because you're bound by this serial portion, 1 minus P, of the algorithm. Okay, so the convoy only goes as fast as the slowest ship. Okay. Hopefully that's all fairly straightforward. Yeah. Okay. So I started sort of writing this slide, and I called it "What's Parallel?" And then I decided actually maybe it's easier to just sort of think about what's serial, because it's sometimes not absolutely obvious actually. So the obvious things are, well, what's serial? Well, our scatter and gather operations have to be kind of done at least notionally in serial, right? My sort of master node has to send its data out to all my worker nodes, and it has to get that data back in order to kind of summarize it. Input output, so writing to the disk or to the screen, passing data down the network even, tend to be serial operations. And there are some kind of wrinkles around that as technology has tried to kind of make this more parallel, but essentially it's a serial process. The other thing that's kind of serial, and it isn't obvious from the code example I've given, is kind of what goes on behind that code as it's interpreted. So if you spawn up parallel processes, there's a time for the machine to kind of load the parallel software library in to set up any kind of communication that needs to go on, set up any threads and do any kind of sort of boilerplate bookkeeping. That's all kind of overhead, that sort of parallel process or parallel thread overhead. And typically we regard that as the serial proportion of the algorithm as well. And in fact, given the number of processes, that serial portion can actually get worse with increased processes, right? Because there's kind of more work to do in bookkeeping and setting up processes and waiting for networks to kind of wake up and that kind of thing. All right. And then what people mostly talk about, and I kind of mentioned this in the sort of hardware examples, is more kind of the communication, the time it takes for various processes to communicate. And as you might expect, kind of processes that are situated in one computer, so your 6-core laptop, has quite a short communication time, though in comparison to the time it takes for a CPU to, say, add 2 bits of data together, it's actually quite long. But then communicating down a network, which it might be a fast network, it might be a slow network, imagine it's a much slower thing. Communicating via a disk, yes, it's done, particularly if you're using a parallel web framework, is really slow. Okay, and particularly if you've got to be asking a database to store and retrieve bits of data. Okay, so communication is typically slow, and the time it takes for processes to communicate, you can think of as kind of serial computation. Okay, so I thought I'd sort of ask a question just to sort of gauge kind of thought process in the audience and gauge experience, really. So supposing I have one of these so-called embarrassingly parallel algorithms. So embarrassingly parallel algorithms, a little bit like our Monte Carlo sampling, are algorithms where we don't really need to communicate during the runtime of the algorithm. Okay, so you could think about this as any kind of Monte Carlo simulation. If it's me, it's kind of simulating epidemics forward in time, and I could give a job to each of 1,000 cores, and those cores would just simulate the epidemic forward in time, and that's embarrassingly parallel. They don't have to share information while they're performing that algorithm. Okay. Now, let's think about, supposing we have a room full of computers, okay, M computers, like next door, and basically we set each computer going, running our Monte Carlo simulation, which might take 10 hours or something. And at the end of that run, each computer is going to write its result to its own hard disk. Okay, we're going to stop there. Right, so what in this case is the serial portion of the algorithm? Is this a completely parallel algorithm, or are there serial elements to it? Correct.
You have a shared memory, maybe?
No, completely separate. Completely separate machine.
Does the fact that you've got to type the same boilerplate code on a computer?
Yeah, absolutely. So some setup time. Yeah. Anyone else? Yeah.
Like I said, the data code that each individual computer is running is something serial.
Yes, that's true, but those serial processes should be running kind of in parallel with each other. Right, yeah. I think the thing that people tend to forget about is it's this second stage. It's the writing of the result. Yeah, that's the hard drive. So it takes time to write, what's potentially a few gigabytes of data that's held in RAM out to the disk. Okay, and we're never going to be able to scale out our algorithm beyond that amount of time it takes to write one simulation to the disk.
If he's writing it onto a separate hard disk.
So yes, but the IO itself is kind of, all those, that chunk of time for which IO is happening, is kind of amortized across all our parallel units, right? In other words, the access time it takes to write, say, a 2 megabyte block, the list is going to be the same for every single computer.
Yeah.
Okay. And even if I'm writing less than 2 megabytes, that access time, that seek time to spin the disk up, find out where we're writing the disk, query the disk index and write that piece of data is going to be serial.
Yeah. So if that's writing a unique piece of data, it's not something that's like
Exactly.
before the start.
That's right. Yes, exactly. Yeah, so I suppose the point here is thinking about parallel algorithms, parallelization, often takes just a little bit of thought as to exactly what parallel versus serial portions of the algorithm are. And okay, maybe the Monte Carlo simulation example was, a little bit obtuse in the sense that actually all those seek time things are just kind of minuscule in terms of the time it takes to do the actual data crunching. But nonetheless, just thinking about those bits, so kind of unavoidable chunks of compute that each machine has to do, that increasing the number of machines will never shorten, is actually what we need to think about in terms of the serial bits of our runtime. Okay. Right, so that's kind of like a really preliminary discussion of parallel computing and the kind of sort of theoretical world in which we sort of think about algorithms. So I'm sure others will expand on this during the week. But I wanted to just have that in mind as we start to sort of think about different kind of parallel computers that are out there. Okay, so this kind of Flynn's taxonomy thing is a fairly sort of famous taxonomy which sort of gets at the heart of trying to describe how a single processor works in terms of its capacity to do parallel computing. Okay, so this is not thinking about, kind of networks of machines connected together. It's not really even thinking about multiple processors. It's thinking about the core itself. And so, when I started computing back in 1986 or something like that, I had a single instruction, single data, 6502 processor in my BBC Model B microcomputer. And it was quite easy to program. You could actually program it in hex machine code if you wanted to, or assembly. And the point was that, if you were running over a for loop or something, you executed a single instruction, double this number, and it did it to a single piece of data. So if you had an array of data, you had to explicitly have a for loop over that array, okay, to compute double the array. And I had to do that as a programmer doing manually. Okay, there was no way that processor could take two numbers and double them at the same time. The serial process. Okay. But what we really have now in, I would say, most, if not all, devices we would consider to be a computer. So everyone considers that to be a computer these days, I hope. Are what are called single instruction multiple data processors. And I suspect that's probably what we're going to be thinking about mostly this week in terms of kind of the practical sessions and doing the stuff with TensorFlow or JAX or whatever we're doing. So SIMD is where a processor, given a single instruction, add 2, square it, take the square root, will act on multiple independent bits of data to perform that instruction. And all modern processors do this. I've got an example a little bit later on of some code which makes this a bit more explicit. And it might surprise you to know that, because particularly if you're an R user or a kind of vanilla Python user, you might be well used to kind of writing for loops that spin over an array of data. Okay, those kind of very high-level languages will give you vectorization in terms of, I have a vector in NumPy or R, and I add 2 to it. That kind of loop over the vector is done for me. But actually, as long as I'm using the right kind of subsystem, the right kind of machine code underneath that interpreted language, I can switch on the SIMD vector engines in my CPU, and I can actually compute in blocks of 4, 8, 16, either single or double precision and floating point numbers at once, and see an immediate and very linear improvement in the speed of the operation. GPUs carry this idea to extreme. Why do they do that? Well, if you think about the screen, well, it's just a matrix, so it's kind of 3 matrices, red, green, blue. And so graphics cards, going back before CUDA and general purpose GPU compute thing, graphics cards were constructed really to do very, very fast matrix multiplications on arrays of pixels, shading them in various ways when you're playing like, World of Warcraft and so on. And they do it quicker than you can actually perceive the screen flickering. Okay. And the sort of realization was circa 2007-ish, that you could actually employ GPUs to do more general types of doing algebra. And that's kind of to the sort of style of GPU compute we do nowadays. Okay, so we'll talk more about SIMD. This is a really interesting one here. Multiple instructions, single data. What the hell is that? I've got one piece of data, an atomic scalar, and I'm using 2 instructions on it at the same time. Why would I want to do that? Well, the best example I could find was the Space Shuttle program. So apparently, on the Space Shuttle, you would have maybe 3 or 4 different ways of computing a result from a bunch of sensors. And you want to make sure that your computational pipeline, possibly even sensors, I suppose, are all behaving sensibly. So what you do is you have a bunch of different ways of computing the result. You create a microchip that sort of encodes that calculation within it, feed the results in, you make sure that the results are equal. And if they're not, you know that there's something wrong with the system, and then great warning lights go. Okay, so I thought that was quite an interesting thing to sort of mention. I cannot imagine that in day-to-day statistics we would be kind of using MISD architectures. What we do use all the time, what we're using here, because we're on Teams, right, is multiple instruction, multiple data systems. And this is typically where you have multiple processors doing different things with different states. So for Amazon, you know, your business is predicated on this kind of network of tightly coupled microservices. That's an MIMD system. So again, I definitely have seen some quite interesting papers published on kind of MIMD systems. I think there was quite a nice paper on sort of distributed MCMC that was published a few years ago that had this idea of a sort of an inference server and then worker nodes, and different parts of the network were doing different things with different bits of data at the same time. But I don't think we'll be talking about that this week. Correct me if anybody. Okay, fine. Right. So we're basically going to focus mostly on this SIMD style of compute, or SIMD architecture. And to just put some kind of visuals around this, I guess, this is, I think this is a Wikipedia slide or something, but it makes the point quite nicely. So yeah, the idea behind single instruction, single data, SASD, is that you just have a data pool and the instruction pool and one instruction per bit of data. Okay. Then the SIMD thing, you'll see various incarnations of this diagram popping up in the next few slides, because it's a very natural thing to think about, one instruction, but several processes which perform that instruction on different bits of data. And that's really the core idea behind GPU compute. And that's range on the CPU success. Okay. So any questions about that taxonomy before I go on? Has anybody kind of heard these taxonomies before? Sort of, yeah, floating around in there. Yeah. Okay, cool. Okay. Now I'm going to conjecture that Flynn's taxonomy is useful to people who design processors. Okay. I'm not sure that it's massively useful to us as kind of statisticians, data scientists, kind of software engaged people. Because I think, most of the time we don't really care about what's going on with the hardware, although an appreciation of the hardware is useful, as we'll see. What we really care about is the execution model. How are our programs executing? And how can we program in a particular model or design our algorithm that fits this particular model of execution? Okay. And I think the best example for this really is this single program, multiple data idea. So you might think, well, what's that? Well, if I've got an HPC cluster, so this is a collection of independent computers connected together with a network, then what I have to do as part of my setup routine when my algorithm starts is to send a copy of the program that I've written to every single worker node in my cluster. Right? And then somehow I'm going to give that program an ID that belongs to the processor, and I can use that ID to select out a bit of data that I then want to run through the program. Okay, and that bit of data could be the ID itself. It could be a group of random seeds. It could be a bunch of genome reads from a genetic, genetic sequencer, DNA sequencer, whatever really. But the idea is that there are multiple instances of this program running on independent computers. But each computer is using a different bit of data. Okay. And that crops up all over the place. So not only just kind of standard HPC clusters that you might have used, but has anybody used Python Dask to do? Yeah, one person. Yeah. So the data scientists, like big data scientists, love Dask. It's an SPMD model for being able to do computation just from a single Python program, which then spawns itself out onto worker nodes. And then this is slightly curious thing here, actually, this multiple program, multiple data model. So what's this? Well, this is an idea where you've got the sort of idea of a manager and a worker, or a server and a client. And they might pass data between themselves, but actually they're running different programs with different things with that data. Okay? And it turns out actually that the processor in the Sony PlayStation 3, I didn't realise this, is exactly this architecture. So it basically has a collection of kind of slightly loosely connected co-processors that do different things depending on what game you're playing. Okay, I haven't looked into this, but it might be like, one processor does the physics engine, is really good at doing floating point. The other one does the graphics, that's really good at doing integer, so on and so forth. Okay.
There's also the use of program as the same for instructions here, is just to say it's something more sophisticated doing.
Yeah, something much, something at a higher level than, just instructions, Now, I guess the wrinkle to that is here, because actually the single instruction, single data and the SIMD sort of architectures are themselves execution models, I would argue. So there's a kind of a one-to-one mapping of those two. But you could imagine that, for like single program, multiple data, well, actually, I could use one instance of the single program with a SIMD architecture and do the multiple data anyway. Or I can use SPMD on a bunch of SISD CPUs in different computers. That's what I used to do on a HPC in Lancaster circa 2006. Okay. Right. So having sort of discussed architectures and things, I thought it might be worth just thinking a little bit about hardware and giving you a bit of an inkling for what's actually going on in the box, as it were. So here's again, it's just a Wikipedia graphic, but I think it's quite a nice summary. So the idea is this. Is that the CPU really has kind of three logical blocks in it. Okay, so it has a control unit, and the control unit is the bit of electronics that is responsible for looking down the list of instructions the CPU is tasked with performing, and scheduling or telling the processor which operation to perform on which bits of data when. Okay. Then inside what you might think of as the processor itself, we've got two blocks. So the first is the registers. And the registers are a tiny, tiny bit of memory that sat inside the processor itself, right next to the combinatorial logic block, which is commonly called the arithmetic logic, the thing that does the the adding, dividing, and multiplying, knots, ands, etc. Does the actual work on the data. Okay. So then the control unit's responsibility is to ensure that the right data gets into the right registers and the right instruction is scheduled onto the ALU, okay, in time for the computation to take place. And then sat outside the CPU,
Register again?
so registers with a tiny bit of memory that's sat right next to the arithmetic logic units. Okay. So if you're programming in assembly code, it's kind of one CPU instruction per clock cycle, then you will be responsible for moving data from the main memory, which sits outside the CPU, the RAM, okay, into the registers. And then the electronic circuits, this is all very physical, very sort of hardware. The electronic circuits between the registers and the ALU will grab those bits of data, and those bits of data, ones and zeros in 8-bit packets, and they will pull them into a circuit which does the addition, or circuit which does the multiplication, or circuit which does. And all of these circuits are within the combinatorial logic, and all those circuits are within the combinatorial. Yeah.
So it's registered some elements with cache.
No, no. I've got a slide on that in a minute, but good question. Yeah, so that's one thing I don't like about this diagram. It doesn't have cache in it. But this is kind of like a, if has anybody done anything with kind of Arduino microprocessors and things? Yeah, Dan. So if you program microprocessors, if you do it properly, you do it in assembly. And microprocessors don't have cache. They have main memory, which sits in like an EEPROM, and you can grab a bit of data, but you have to move it into a register before you can get the processor to do anything with it. Okay. This kind of architecture, so nothing's perfect in engineering, and this kind of architecture introduces what we call bottlenecks. And I think the two most important ones here are kind of contention for memory. So supposing we had several combinatorial logic units within the processor acting in parallel, but actually they all wanted to access, like a constant, which was out in RAM. You can imagine that they're all trying to compete for the same bit of memory. And if we don't do something special, then there's going to be a queue. That means that those memory accesses have to then be serial and parallel algorithms destroyed. Okay, so we need to think about memory contention. The other thing that we need to think about is kind of instruction contention. So it's not so much contention, but it goes back to Envoy being as fast as the slowest ship. Some instructions, multiplications or notably divisions actually, take multiple clock cycles. Whereas an addition operation, addition of two integers, for example, just takes one clock cycle. So then maybe one processor is going to have to sit around kind of twiddling its thumbs, spinning, doing no-ops until that slower processor or that more complicated algorithm finishes. So there are kind of sort of considerations, design considerations we might want to think about at this level. And again, this is not hugely relevant to us on a day-to-day basis as kind of scientific programmers. Definitely worthwhile thinking about if you're an engineer. Okay, so how have kind of processor engineers, processor manufacturers tried to alleviate this problem? Well, I don't want to go too deep into this, but again, it's just worth sort of knowing about the general kind of what's going on in my machine. Well, the old 6502 processor in my BBC would be called a subscalar processor. So the idea about a subscalar is that if I had three instructions I was trying to process, so one instruction is represented by each of these three blocks, and we have various stages of processing an instruction. We have to fetch the instruction, decode it, to know what it is, and what bit of electronics we need to invoke to run it. We've got to get some data in. We've got to execute the instruction. We've got to write the result back to the register, etc. Okay. And the subscalar processors really were kind of designed to process one instruction per clock cycle. Okay. Now, what's a clock? So a clock is a pulse that's applied to your CPU, and on either the leading edge of the pulse or the trailing edge of the pulse, something happens. That's how it kind of works. So when you say, oh, I've got this whiz bang new kind of 3.8 gigahertz processor in my gaming machine, that's the clock speed. Okay. So that's what we're talking about, the clock. So instructions happen on the clock. Okay. So you're kind of then limited by your gigahertz, but we all know that processors are getting faster without the clock frequency again. So what's happening? Well, it turns out that there's this idea of something called instruction pipelining, where we say that actually, the bit of the CPU that does the instruction fetch, the decode, the execution, fetching memory from registers, etc., those bits are kind of serial, but there's no reason why they have to be serial. Kind of like the instruction fetch is sat idle while the previous instruction is being executed. No reason why it has to be sat idle. it could actually be prefetching the next instruction. So the idea behind pipelining is to kind of overlap these sequences of electricity that's going on in the CPP. Okay, so that we can actually process multiple of these pipelines together, albeit in a sort of staggered fashion. Okay. So you can think of that as like, you know, being like a car production line. You know, you don't kind of sort of invoke a production line and just make one car as it moves through. That's silly because, you know, the people who make the seats are sat idle while the engine's being made. You don't do that. You kind of production line your car so that actually actions are happening in parallel, just on different units as they move through the pipeline. And then combining that idea of instruction pipelining with the idea of, again, SIMD computation, you get the idea of these super standard processes, which we all have in our machines these days. Okay. So again, we don't have to think about this on a daily basis. You might want to think about it if you're an extremely low level kind of engineering level programmer. Or a hacker trying to kind of do Spectre and all that kind of stuff. Okay. So vector processing, and so I mentioned kind of, you know, modern processors, well, since 1997. Who in the room remembers the MMX kind of boom in 1997? Yeah, Dan does. I do. Yeah. Okay, so this was the greatest thing at the end of the 90s. MMX processors that you could play Doom faster on. And the innovation was to really introduce this SIMD technology into the processor itself. Intel did it first. Well, I swear to it. No, I think Cray did it first, actually. Some of the earliest Cray supercomputers, I think, were SIMD in the processor themselves, but they were fairly special. You didn't have one of those at home. Intel, I think, were the first to do it for home market.
But is this meant to be like a Pentium 1 or is it something?
No, it's after Pentium.
After,
Yeah. Pentium introduced the pipelining.
okay.
And then the MMX. So the MMX things were all supposed to be multimedia. You can see where this is going in the days slightly before graphics cards. When you wanted this better processing the graphics. If you want to use these vector processors, it's not an automatic step. Okay, so I think GCC C compiler has got better in the last few years. Goodness knows what Rust does. But certainly when I was doing these kind of experiments, probably about 5 or 6 years ago, if you wanted to use vector programming in your C code, you had to actually manually use these kind of vector extensions that GCC gave you. So, so this is a computation. Really, it's not very interesting. It computes the square root of a product of 2 squared numbers. And you have to manually load your data for each of those numbers, A and B, into, well, we've got our vector registers. Okay, our MMX registers. So now I'll register a tiny bit of memory. It doesn't just hold a scalar bit of data, but it holds a vector of data. And then I have to invoke instructions which are specified vector instructions for each of those registers. And so I've actually got to get quite close to the metal. If you compile this code and stop GCC halfway and get it to spit out the assembly code that it sort of produces from C before it actually produces the ones and zeros, you can see what's kind of going on. And all of these XMM flags here, or references, are references to the multimedia extended multimedia registers that sat there next to the processor, next to the vector unit processor. And then all the instructions that we're invoking on those vector registers are all prefixed with a V. So these are all vector operations that we're performing. Okay. Ideally, you don't want to have to do that, I would suspect, in your day-to-day operation. The other thing is, this is a kind of an AVX2 instruction set, like 2013, 14, I think, something like that. If I wanted to use this code on an older processor, I would have to rewrite it to use kind of 128-bit or 64-bit MMX registers. So, it takes me a bit close to the metal. I don't want to be doing this on a day-to-day basis. It's a pain. It's a pain when I give my code to a mate who's got an old machine and it doesn't work.
Then just quickly, because you're doing 56 minutes, so you want to go to the hour and like do short.
Why not? Sounds good. Okay, yeah, actually, that's good. So just one more slide, and then that's a good stopping point. Okay, so I just wanted to talk about something called the memory wall for the break, and then I'll come back to the cache question that Tamas asked earlier. So thing to remember is that processors are so fast now that all the arithmetic logic operations that go on with it are typically much faster than the time it takes to fetch some data in, even from the RAM. Okay, that might be surprising if you've never really thought about this before, but even though it's kind of like appears like a direct fetch out of the RAM, you've still got a memory controller to pass. There's an address translation that goes on to tell you where the bit of data is. You've got to pull it through. You've got to kind of compete maybe with other processors that are trying to use the memory controller at the same time. Fetching memory from RAM is quite slow, and typically we're talking of the order of more than about 100 processor cycles, more than 100 politics. Whereas, multiplication can be only one clock cycle. So what we risk here is this kind of memory starvation. I think particularly for the sort of algorithms that we use, where we've got a relatively big data set and a fairly complex algorithm. My feeling is that most of the stuff that we work on is what's called memory bound. So it's getting the data in and out of the processor that's the challenge. And you can use a SIMD processor, which just hooving in data, this problem's exacerbated. And so what we hit is this thing called the memory wall, where our processors sitting around waiting for the memory controller to do this in the field of the next bit of data. Okay, so there's a limit there. That memory fetch is in effect a serial operation. Okay. Memory caching, L1, L2, possibly L3, which all the gamers kind of study and buy the next expensive processor and that kind of thing, comes to the rescue here. Let's have a 5-minute comfort break. Chat now afterwards.
Quick round of applause for professional. Guys, we are taking a picture outside, given it's sunny. So can we do that straight away before coffee?
Just when you online, should we start again in 10 minutes?
10 minutes? Yeah, why not? Yeah.
So yeah, forgot people online.
For people online, yeah, we are starting in 10 minutes, okay?